Welcome, viewers, to the fifth and the last segment of the sixth lecture for the online series of lectures for the course of Algebraic Topology 1. In this last segment, we are going to review some basic aspects of abelian group. An abelian group is free if it has a basis. What does it mean? What does it mean by a group having a basis? That is, if there is a family G alpha, where alpha runs in the index set J, if there is a family of elements of elements of G such that each G in the group G can be written uniquely as a finite sum G equal to sum over all n alpha G alpha. Okay, it's going to be a finite sum, meaning that there are finitely many terms in this summation. Okay, this is our equation number 10. Okay, it means, let me write it here, there are finitely many summands here. There are finitely many summands here. Okay, all right. So the uniqueness of this expression 10 implies that each element in the basis element G alpha, or more generally for any non-zero element in the group, has infinite order. Okay, that is, each of such basis element G alpha generates an infinite cyclic subgroup of G. Infinite cyclic subgroup of G. Okay, so let us try to prove this. Suppose the contrary. Okay, we proceed by contradiction. That is, there exists a natural number such that n times G alpha is equal to 0. Then, so if this is the case, then using the uniqueness uniqueness of the expression 10. Expression 10, one writes G alpha uniquely as G alpha is equal to 1 times G alpha. Okay, so that n times G alpha is equal to n times 1 times G alpha. Okay, which is nothing but n times G alpha, and hence n times G alpha is equal to 0 will imply n is equal to 0. So n is the order of the element G alpha of the group G, means that n times G alpha is equal to 0, right? And from the uniqueness of the expression 10, it implies that whenever we have n times G alpha to be 0, we must have n to be equal to 0, right? So we arrived at the fact that there is no positive natural number for which G alpha is annihilated. Meaning that G alpha has infinite order. Okay. Okay. So this is the story of a free abelian group. Okay. More generally, if G in big G can be written as a finite sum, G equal to sum over all alphas in the index set J, n alpha G alpha, but not necessarily uniquely. Then we say that this family G alpha, as alpha runs in the index set J, generates G. Okay. In particular, if the family that we are talking about is a finite one, if the set G alpha is finite, we say that G is finitely generated. Okay, finitely generated. So in the case of a finitely generated abelian group, we don't expect the group elements, will be written as a unique linear combination of the elements in the generating set. Okay. So that's the difference between finitely generated abelian group and finitely generated free abelian group. Okay. Whenever we have a finitely generated free abelian group, it's guaranteed that the expression 10 that we talked about earlier, that each element is expressed as a linear combination of the elements in the generating set. Okay. If it's a free abelian group, then this expression is a unique expression. And if it's just a finitely generated abelian group, then we don't expect this expression to be a unique one. Okay, good. Now, okay, let me erase everything. If G is free and has a basis consisting of n elements, if G is free and has a basis consisting of n elements, say G1, G2 all the way up to Gn, then every other basis will have the same number of elements in it. Every other basis for G consists of precisely n elements. Okay. Let's see how it works. How this, let's see how we prove it. Now, we write this at 2G, which is the collection of all elements of the form 2 times G, such that G is in the group big G. This is easily seen to be a subgroup of G okay. So one can check that it's a subgroup immediately. An arbitrary element, we take an arbitrary element 2G in this set 2 big G, 2 times big G, that can be written uniquely as as 2G is equal to 2 times sum over all the i's running from 1 to n, mi with mi being an element in the set of integers, okay, where G and G has the form G is equal to sum over all mi gi, where I runs from 1 to n. Mi is in the set of integers. Okay, so this is how we write an arbitrary element of this subgroup of G. Okay, now the group G quotiented out by 2G consists of cosets, okay, we know from elementary group theory that this is a group whose elements are cosets. The elements of which are of the following form. Okay, so the elements here in the cosets are of the following form. From I equal to 1 to n, 2mi plus epsilon I times gi, where mi belongs to the set of integers and epsilon I are either 0 or 1. Okay, so if all the epsilon i's are 0 for I from 1 to n, then so let us call this equation 11. Okay, so if all the epsilon i's are 0 in 11, epsilon I can be 0 or 1. Okay, but in the case where all the epsilon i's are 0 in 11, one gets the representative here. It is a representative of the coset, of one of the cosets here. Okay, so so for different cosets we have different representatives. So if I take certain choices of epsilon i's where I run from 1 to n, we get a representative of one of the cosets. Okay, so so in the case where epsilon I is identically 0 for all i's, I from 1 to n, we get a representative of the coset 0 plus 2g. So a representative of this coset is of the form 11, where all epsilon i's are 0. Okay, I running from 1 to all the way up to n. Okay, so how many representatives we can choose from here? There are n epsilon i's, right? I runs from 1 to n, and so there are two possibilities one can choose for each epsilon I, right? Either 0 or 1, and there are n such pairs. This is the first pair, there is a second pair here, there is a third pair here, so all the way up to n there is an nth pair here. Okay, and each of these pairs can be chosen in two ways. So how many ways it can be performed? 2 to the n ways, right? So that's why you have 2 to the n representatives altogether, and each representative is a representative of a coset. Okay, so we see from which we see that this group has 2 to the n elements, right? Now, so we computed all these things starting with this basis, right? G1, G2 all the way up to Gn, right? And we assume that this basis consists of n elements. So if we choose another basis, G prime 1, G prime 2 all the way up to G prime m, so that there are m elements in this new basis, then we'll end up with the fact that the cardinality of this group or the quotient group is equal to 2 to the n, all right? But it's the same quotient group, right? So 2 to the m is supposed to be the same as 2 to the n, which gives us m to be equal to n, which means that this m cannot be different from this n. In other words, two bases of the free abelian group, that of the free abelian group that we started with, okay, cannot have different number of elements in them. They have to have the same number of elements. Okay, so the number of elements in a basis, so we have seen that whichever basis we choose for the group, for the free abelian group, a basis has to consist of the same number of elements. Each basis has to consist of the same number of elements, and the number of elements in a basis for G, the number of elements in a basis for G is called the rank of G. Okay, good. All right, so we are done with the notion of the rank. Now there is a specific way of constructing free abelian groups. Let us discuss about this construction very briefly. Okay, so the story starts with a generating set. We are given a set S. Okay, we define the free abelian group G generated by S to be the set of all the functions, to be the set of all functions phi from S to the set of integers Z. Okay, so the group to be generated, the free abelian group to be generated out of this set S is considered to be the set of all functions, functions from S, the generating set itself, to the group of integers, to the additive group of integers. Okay, such that phi of x is equal to 0 for all but finitely many values of x in S, for all but finitely many values of x in S. Okay, so for all other points of x in S, phi of x is going to be non-zero. Okay, so addition of two such functions phi and psi is given by in a straightforward way by pointwise addition. Phi plus psi evaluated at x is going to be equal to phi of x plus psi of x. Okay, this is our equation number 12. Now, given x in S, the characteristic function phi sub x for the x in S is defined as phi sub x evaluated at y is equal to 1 if a y is equal to x and is 0 otherwise, okay, if y is not equal to x. This is equation number 13. Now we have seen that the group G, the finitely generated free abelian group G is, you know, I should not say finitely generated. It's the free abelian group generated by the given set S. Okay, is taken to be all functions phi from S to Z such that phi at any point is non-zero for only finitely many x in S. Okay. Okay. So now I need to find a basis for the set of all such functions. Okay. And one can check that this forms a basis for this set of functions phi sub x, okay, for x in S. This is the collection of all characteristic functions on x in S. Okay, this forms a basis for G. Forms a basis for G. You know, if a given function in G, one can write it as a finite sum. Okay, phi is equal to nx phi x, okay, where x is in S and such that phi x is not 0. You know, there are finitely many x's on which phi of x is non-zero, right? There are finitely many such x's, okay? So you sum over all those x's, okay? So that's why it's a finite sum. And this is our equation number 14. So using 13, that is the expression of the characteristic function, one obtains from 14 that phi of x is nothing but n sub x, because phi sub x evaluated at x is 1, which follows from the definition of this characteristic function. Okay. And the summation in 14 extends over all x for which phi of x is non-zero, which we have written down here. That is why this sum is a finite sum. We have seen earlier that G is an abelian group. Okay. And an element G in the group has finite order if ng is equal to 0. What is ng? Ng is nothing but g added to itself n times. Okay, and g added to itself n times results in 0. And then we say that if this results in the identity element of the group, and if this is the case, we say that the element G is of finite order. Okay, so the set of all elements of finite order. So we have a group G and we pick up all the elements in it which are of finite order. We take the collection of all such elements of finite order of the group, and that forms a subgroup of the given group, and it has a name. The name for this subgroup is torsion subgroup. Torsion subgroup. Okay. So we pick up all the elements of finite order from the group, and the collection of all these elements of finite order is a subgroup of the given group called the torsion subgroup. Okay. And it's denoted by T. A torsion subgroup T is denoted by T. Okay, so if T vanishes, if there is no element in the group of finite order, we say that the group is torsion free. Okay, so we have seen earlier that in a free abelian group, no non-zero element is of finite order. Okay, it follows from the uniqueness of the expression of a non-zero group element, written as a linear combination of the basis elements. So from the uniqueness of that expression, it follows that no non-zero element of the group is of finite order. So whichever element we pick up from the group, which is a non-zero element, by non-zero element we mean that it's not an identity. It's not the identity element. So if you pick up a non-zero element, then that element is of infinite order. So this is the case of a free abelian group. So which means that a free abelian group is necessarily torsion free, the converse of which is not true in general. Okay, so let me write it. A free abelian group is necessarily torsion free okay, the converse is not true in general. True in general, meaning that there can be torsion free groups which are not free abelian. Okay, true in general. So this is an exercise. Find an example. Find an example of a torsion free group which is not free abelian. Okay. All right. Now the notion of direct sum. Suppose G is an abelian group. G an abelian group. Okay. And suppose G alpha, where alpha runs in an index set J, is a collection of subgroups of G. Collection of subgroups of G. Okay. Further, suppose each G in the group G can be written uniquely. It's important. It has to be unique. Uniquely as a finite sum. Sum has to be finite as well. Finite sum. G is equal to sum over G alpha, where each G alpha belongs to big G alpha for all alpha in the index set J. Okay, then G is called, then G is called the direct sum of the groups G alpha. Okay, so this is the notion of direct sum, and we write it in the following way: G is the direct sum of all G alphas where alpha runs in this index set J. Okay, we call it equation number 15. And in the case when this collection is a finite collection, okay, something like this, G alpha is equal to G1, G2 all the way up to Gn. So there are n such subgroups of the group G. Okay, one writes the direct sum in the following way: G1 direct sum, G2 direct sum all the way up to Gn. This is 16. Okay, good. Now more generally, if each G in the group in the abelian group G, big G, can be written as a finite sum, written as a finite sum, G is equal to sum of G alpha with each G alpha belonging to big G alpha for all alpha in the index set J, but finite sum expression not necessarily unique. But the finite sum expression not necessarily unique. Then G is just called a sum. The direct does not apply. G is called the sum of the groups. The sum of the groups G alpha, as alpha varies in the index set J. And one writes this fact that G is the sum of all this, the sum of all the elements in this collection as this: G is equal to sum over all G alphas. Or in the finite case, as G is equal to G1 plus G2 plus all the way up to Gn. This is equation 17. All right, so what extra condition that we have to put on the sum of a bunch of subgroups of the given group? So if you want to declare that G, so if you have G as the sum of a collection of its subgroups, then what extra condition do you have to put in there so that this sum can be termed as a direct sum? That's the thing. Okay, so let's see. If G is equal to the sum of all G alphas, where alpha runs in the index set J, then this sum will be direct. Okay, or in other words, this expression will be unique if and only if for each fixed alpha 0 in the index set J, G sub alpha 0 intersected with the sum of G alphas, we have to exclude alpha 0 in this sum, okay? And take the intersection, and that has to be the identity element only and nothing else, okay? So there is no non-trivial overlapping between this, the elements, between the elements in this collection. Okay. So this is the sum over all G alphas where alpha is not equal to alpha 0. Okay. So we take a mutually disjoint, mutually non-trivially disjoint. Disjoint does not mean that they will always have this identity element in common because they are subgroups, right? But there will be no non-trivial element in the intersection. Okay, so what connection does this concept of direct sum have with free abelian group? Okay, so let's see. Connection with free abelian group. If G is free, then it has a basis, right? Then it has a basis, say G alpha. Okay. Then all these basis elements, G alphas are of infinite order, right? We have seen it earlier, are of infinite order. Okay. The subgroup G sub alpha that G alpha generates, okay, is infinite cyclic, okay, because G alpha is of infinite order, so the subgroup that it generates has to be infinite cyclic, right? Infinite cyclic, and big G is the direct sum of the subgroups, of these generated subgroups G alpha. Okay. Conversely, if G is a direct sum of infinite cyclic subgroups, then G is a free abelian group. G is a free abelian group. Okay. Now the last theorem of today's lecture, which is a very important theorem. Let me erase everything to state this theorem. I'll not prove it. Okay. Theorem 2 which is known as the fundamental theorem for finitely generated abelian groups. The fundamental theorem for finitely generated abelian groups. Okay. All right. So here is the statement. Let G be a finitely generated abelian group. Finitely, we don't need the freeness. We just need the finite generation thing. Finitely generated abelian group so that it has a finite set as a generator. Let T be its torsion subgroup. Okay, torsion subgroup. Since it's not free, we can have torsion elements, right? We can have elements of finite order in the group. A, there is a free abelian subgroup. Since it's not free, but there is a free abelian subgroup, free abelian subgroup H of G having finite rank beta, okay, meaning that if we can choose a basis of this free abelian group, the basis having beta number of elements in that set, and that's why this free abelian subgroup has a finite rank beta, such that one can write G as the direct sum of H and the torsion subgroup T. Okay, that's part A. And part B tells us that there are finite cyclic groups T1, T2 all the way up to Tk, where Ti has order Ti greater than 1. Okay, and what's the order of a subgroup? It means that there are the order means the number of elements, the cardinality of the group. Ti has order Ti greater than 1. The number of elements in Ti such that Ti divides Ti plus 1, right? For each I in this finite set, 1 to all the way up to k minus 1. And this torsion subgroup T can be written as a direct sum of these k subgroups of the torsion subgroup. Okay, that's part B. Okay, now what does part C tell us? The numbers, part C is also important, the numbers beta and T1, T2, Tk, which are the orders of the corresponding cyclic groups T1, T2 all the way up to Tk. these these k plus 1 numbers, there are k numbers here and there is this beta, these are uniquely determined by G, determined by the the finitely generated abelian group that we started with. Okay, so these are the three parts of this very important theorem. Then we have a few comments on this theorem. The number beta is called the Betti number, the Betti number of G. The numbers T1, T2 all the way up to Tk are called torsion coefficients, torsion coefficients of the finitely generated abelian group G. Okay, torsion coefficients. Okay, now we can we can further improve this theorem. It's not improvement, we can reduce it further by noting that prime factorization of the order of the torsion subgroup of G, torsion subgroup of G. Okay, and there is a very important result from group theory that tells us that Z quotiented out by mz. Okay, so the additive group of integers modulo addition modulo m. So this finite group direct sum Z quotiented out by nz is isomorphic to Z quotiented out by mnz, and this only holds when m and n are coprime. Holds when m and n are coprime. Okay, so using this fact and the prime factorization of the order of the torsion subgroup leads us to the fact that G is isomorphic, the finitely generated abelian group is isomorphic to the beta fold direct sum of Z, which is the free part, is the beta fold direct sum and then we add the finite part, the torsion part, okay, which is Z sub a1. Okay, so Z quotiented out by mz is also written as Z sub m. Okay, so Z sub a1 direct sum Z sub a2 all the way up to Z sub as. Okay, so it's if the order of the torsion group is T, then we write T as the multiplication of a1, a2 all the way up to as, where a1 is some prime p1 raised to say k1, and a2 is p2 raised to k2 all the way up to ps raised to ks. Okay, where p1, p2, ps are all prime. p1, p2, ps are all prime numbers. So this is the prime factorization of this number t. Okay. Okay. So this is a refinement of the finitely of the fundamental theorem of finitely generated abelian group that we discussed earlier. So now that we are almost at the end of the sixth lecture, let me list a bunch of exercises for you. This is very useful if you this will be very useful if you go over the exercises. The book that we are following for the contents that we are having currently is Elements of Algebraic Topology by Moncrief. Okay. This is the book that we are following. So section 1, you need to do number 1, number 2, and number 3. Section 2, you do number 1 and number 5 only. Okay. And for section 4, try these 3 problems, number 1, number 2, and number 3. Okay. So this is the end of lecture 6. Thank you for attending the 6th lecture.